Dear students, let us again begin with the concept of ILD and the moving load. In previous lecture, we have learned how to draw influence line for a point load for the shear force variation. So, if you are given with the point load W along the span, you may given with some section XX from the left side, so that the remaining span is L minus X. So the ILD variation is like this for shear force, because when the load approaches towards here, the reaction at A will be more. The reaction at A is positive shear force because of the sign convention. If you consider a section left side upward, so RA support is towards upward. So RA is considered to be positive shear force and the RB is considered to be negative shear force because it is opposite in this direction at B. So the positive shear will be maximum when the load is placed here. When the load is moved further from left to right, the positive shear decreases. At the same time, negative shear force will be increases up to the particular section. So this is the shear force variation diagram, ILD diagram. Okay, so we can calculate maximum positive shear force by superimposing the load W here and by calculating the ordinate value, which is L minus X by L. This ordinate value is X by L. So if you multiply the load into the ordinate value, you will get the maximum positive shear force. At the same section, if you multiply the load with X by L, you will get maximum negative shear force. So this is at particular section, at a section. If you want to absolute maximum positive shear force, the possibility of placing the load is only at A to get the maximum positive shear force, because if you try to place at any other section along the span, it will give the value lesser than this RA, because RA is maximum when the load is placed at A only. So the absolute maximum positive shear force, the absolute value, absolute maximum positive shear force occurs when the point load is placed at A. When the point load should be placed directly over the support, directly over the support A. Point load at A. Okay. This is for absolute maximum positive shear force. For absolute maximum negative shear force, the same concept is applied here. When the load is just started at A and it is going to be leave at B, means the load should be placed at B. So the reaction at B will be maximum when the load is directly over the support B. The value of reaction RB is always negative because of the sign convention. So the absolute maximum negative shear will be the negative diagram of the W. W equal to, here if it is ILD diagram. If it is ILD diagram, this diagram will be having a magnitude of 1, and if you superimpose the load over the support A, W, W into the ILD ordinate, which is equal to 1, which is equal to W kilonewton, it's the maximum absolute positive shear force. Similarly, the ILD ordinate, the maximum ordinate is equal to 1, and if you are applying the load at the support B, W into ILD ordinate, which is W into 1, will give W kilonewton as the maximum negative shear force, absolute maximum negative shear force. So we have learned to draw the shear force variation, maximum positive shear force at a section and maximum negative shear force at a section and absolute maximum positive shear force. For this criteria, we need not having a section because it is absolute value, maximum of maximum value. So the only possibility is locating the point load over the support. If you are needing positive shear force, you have to place the load over A. If you are having the maximum negative shear force to be calculated, then locate the point load over the support B. So these are the points we have studied, and again I am recalling. Now we are going to understand the ILD for bending moment. It is also very simple. This is ILD for bending moment concept. There are only two bending moment variation diagrams. One is this shear force variation diagram, another one is bending moment variation diagram. And consider a simply supported condition with a point load at a section, and we have to place the critical load over the section to draw the ILD. So we have placed W, and we know the bending moment variation for a point load in a simply supported beam, that is triangular variation. For UDL, it will be a parabolic variation. For a point load, we know the bending moment variation is a triangle. If it is X, if it is L minus X, we can analyze the beam. We have located W at a section X, here L minus X. We know RA value. Before in the previous lecture, we have calculated into W. So this is RA, RB equal to X by L. If you want the bending moment at this section, under the load or at this section, we can either calculate from RA and RB. I am going to consider RA. So RA into X distance will give the bending moment under the load, or RB into L minus X will give the bending moment under the load. So I am going to consider RA into X. So the bending moment at Xx or under the load is equal to RA into X. We know RA is equal to W into L minus X by L into X. So what is the formula? W by L, X into L minus X. So this is the formula for bending moment at Xx under the point load. In ILD diagram, in ILD concept, we have to consider W equal to 1. Then the ordinate of the bending moment variation diagram equal to X into L minus X by L. So here this should be the ordinate for the maximum value, that is X into L minus X by L is the bending moment ordinate. Here, in shear force variation, the ordinate for negative shear force is X by L, and the positive shear force at a section is L minus X by L. For the bending moment, it is X into L minus X by L. So this is the ILD for bending moment. Very simple concept. So this is the second diagram. Only two diagrams are available in shear force variation. One is shear force variation and another one is bending moment variation. It is also very simple because it is considered simply supported with the point load. Here also simply supported with the point load condition. So with these two diagrams, we can solve many number of problems with some specific conditions. Let us understand what are the conditions to be applied to get maximum negative shear force, positive shear force, absolute maximum shear force for different loading conditions. Here we are talking only about a simply supported with a point load. Next case, we are going to understand the simply supported with a UDL. With a UDL, I am hanging the load because it is a moving load. We don't know where it is going to be placed for a particular conditions, whether we have to get negative shear force or positive shear force at a particular section or some maximum of value at a particular section, the different conditions will be there. So we have a span L for the beam AB, and we have some UDL of span. We can have it is C. The span of the UDL is C, and this loading is categorized under UDL shorter than the span. Shorter than the span. So these conditions will exist in bridges where the small vehicular loading smaller than the span of the bridge traveling from left to right is the case. The example case, you have to imagine a small truck is passing from left to right over a very large span of bridge. So in this UDL, we should identify the head of the loading and tail of the loading for our convenience, because we are considering the load is traveled from right, left to right side. So in our problem, we have to verify whether the load is traveling from left to right or right to left. 90% of the problems will be on left to right only. If you are having some problem right to left, the total concept will be reversed, the total concept. So now we are going to thorough with only one concept, that is left to right, uh, for better understanding. So the load is always traveling from left to right, which is our consideration. Then the head will be like this and tail will be at this point. So where the load is first approaching, at this point. Actually, more the point will be away from the starting point. The head will touch at A and the tail will be beyond the support A. Okay. Then in some point of time, it will come inside the span and some span will be on the outside. After some time, the overall span will come inside and the tail will be on support E. And some more time, the load will be somewhere along the span with head position here and tail position here. After some time, the load will approach the support B where the head is here and tail is here. Okay. So these are the possibility of traveling of the load. And we can understand in a point load problem that if a load is totally located on a support A, we will have absolute maximum positive shear force. But here, if the load is, the starting point is at A, there is no meaning of having total load at A, because more magnitude of or more span of the load is away from the support A. So the maximum absolute positive shear and the maximum absolute negative shear will not be calculated in this case. Rather than we can calculate uh, maximum positive shear force at a section, maximum positive shear force at a section, which is x distance from A, or maximum negative shear force at a section, or maximum bending moment at a section. So in a particular given section, we can calculate these three parameters. And each parameter will have different conditions. Before going to the condition, so I have to clear one thing. Now consider a simply supported beam under section, under particular section at the x distance. If you take point load, for example, if your point load is directly located at A, the reaction at A will be maximum, and also the shear force at A is maximum, where RB is 0 here. This is a general trend. Okay. If in the next stage, the same section, the load is just moved to the right of E. Okay. Now, what is the shear force at XX? Your previous experience in structural analysis will help to calculate the shear force at XX. You have to consider reaction A minus W equal to the shear force equation at XX. It is from the left side. It is from the left side. So RA minus W is the shear force, and from the right side means it should be equal to the RB value because there is no load here. If you consider the right side, RB is the shear force up to the section XS. If you consider left side, RA minus W is the shear force. So your RA value in this case is absolute maximum of maximum value. But when you are considering this case, the RA minus W, because the shear force is reduces to the value of W in this case. So you will have the reduction of shear force when the load moves from left to right apart from the support A. In the next case, the similar result will occur when the load is just left to the section XX, and if you have the reaction RA, here also the shear force at XX equal to RA minus W. RA is the reaction, W is the load up to this section, RA minus W is the shear force equation, and from the right side this value should be equal to minus RB, should be equal to minus RB. Okay. And in this case, the RB equal to 0 because overall the load is located at A. But in this case, the RA will be decreased. Similarly, the RB will slightly develop or slightly increased. In this case, RA minus W will exist and also RB will somewhat not 0, but it will be somewhat lesser value. Okay. Then the next case, consider the load right of the section. Consider the load right of the section XX. Now, from the left side, the shear force is directly RA. The shear force is directly RA, and from the right side, the shear force is RB minus. If you give RB minus sign, depending upon its sign convention, minus RB plus W. So from this diagram, the left of the section is RE. It is fully available. It is fully available. But on the right side of the section, RB is decreases to a amount of W. The RB values decreases, and here the RA value will be increases. So we can come to a conclusion that if the load is placed on left of the section, we can have full RB without any reduction. And if the load is placed on the right side of the section, we have full RA without any reduction. So we can make a condition to have maximum positive shear and maximum negative shear here. So maximum positive shear is always the calculation of RA because of the sign convention. And maximum negative shear indicating the value of RB because of the sign convention, because it is upward left side from the section, and here it is a right side from the section. The existing direction is right side upward, but the positive sign is right side down is positive, so we put RB is negative. So if you want to calculate maximum positive, you need to find out RA value. If you want to calculate maximum negative shear, you need to find out RB value. And if you want to get maximum value, which figure is suitable to get the maximum value of positive shear force? Here you have some reduction of RA minus W. So this figure will not be valid to get maximum positive shear. But consider this figure, the load is traveled to the right of the section so that the RA will not be reduced. RA will not be reduced. It will have its full value. So the condition, the load should be right of the section, or in case of UDL, we have head and tail. You draw a simply supported beam and the section XX. We need to get full RE. Then there should any load in this X distance. There should not be any loading placed in this distance X. The load should be away from this section. So how we can place? If the load is placed like this, we have full RA value. How we can place the load? Our movement from left to right is not varying. It is constant for all problems. All problems are assumed to be the load is moving from left side to right side. So how we can place this load? So place the tail on the section so that the head is on front, so that there is no load on this span X, so that we get RA as a full value. So this is the condition for maximum positive shear. What is the condition? Place place the tail on XX, place the tail on XX and calculate RA value. Place the tail on XX and calculate RA value. I am insisting to calculate RA because we need only positive shear force. The positive shear force is only RA. How we can get RA as a maximum value? The load should not be deducted in its equation. RA minus W, it should not come like this. We should get full RA so that the load should be placed away from the section. How we can place? We can't place randomly. So place the tail of the loading at the section so that the head will be front. So this is the condition for maximum positive shear. So in same way, if you want to get full RB to get maximum negative shear, you consider a section. We want full RB value here to get maximum negative shear. So the load should not be located at this distances, so that the load will be located like this. So here the movement of the load is from left to right, so that the head will be placed at the section, the tail will be on the back side. So for the maximum negative shear force at a section, place the head on the XX section and calculate RB. This analysis will not like the basic analysis procedure. In basic analysis, you calculate both RA and RB, both negative shear and positive shear. In this case, if you want to calculate positive shear force, you should calculate only RE, or you should calculate only RA value, not RB value. You should not calculate RB value in this case. It will not be maximum value. RA is only the maximum value when you place the tail on the section. If you ask to calculate maximum negative shear force, you just calculate only RB value. You should not calculate RA in this case. Okay. Now we clear about the shear forces, maximum negative and positive shear forces, and the location of the loading condition for the UDL. And the maximum bending moment for a particular section means we can discuss both point load as well as UDL here. We know the ILD diagram. I am hanging the point load here. For bending moment, it is the variation. so that the ordinate is x into L minus x by L. This is the ordinate. The condition is place the critical load on the section. The condition for maximum bending moment at xx distance is place the critical load. The critical load is the main point here because we are practicing with a point load, but there are many loads here. UDL shorter than the load, UDL longer than the load, and multiple point loads are there. So the hint for this condition is critical load. We have to identify which load is critical when there is a multiple point load. If there is multiple point load and combined with UDL, you have to locate which one is the critical load. So the general condition is place the critical load on the section, place the critical load on the section and find the bending moment under the load, under the critical load. It is also very much important. Under the load is also very much important because in this case, you may calculate the bending moment under the section also, but it should not be like this. You should calculate the bending moment value under the critical load only, not under the section in any of the cases of different loading condition. You should calculate the bending moment under the critical load. So place the critical load. This condition may vary for different loading condition, but the calculation of bending moment value only under the critical load unless otherwise specified with a different condition like calculate the bending moment under the critical section or under 100 kilonewton load or under the 50 kilonewton load. Otherwise, you have to calculate the bending moment value under the critical load only. Okay. So if for our case, it is a UDL smaller than the span, having the span of C. Here total length is L and we have uh, the separation of the section X and the L minus X. Here the condition to find out maximum bending moment under the section XX, under the section XX. So a simple logic is followed here. Here the section divides in the ratio of x and L minus x. The section divides the total span as x and L minus x on left side and right side. So you have to split the given UDL in the same ratio as the section divides the span. I think you understand the sentence. You have to divide the given UDL in the same ratio as the section divides the span. It divides the span as x and L minus x, so that you give a name for this UDL. You give a name for the UDL is A. This length is A. So the remaining length is C minus A because the total span for this UDL I have mentioned as C. So left side some distances I mentioned as A. Right side remaining distance is C minus A. So you have to divide the given UDL in the same ratio as the section divides the span. So x by L minus x equal to A by C minus C. So in your problem, x is known value, L is known value, and C also known value. So you can find what is A. What is A? So further you can place the load accordingly. You mention, you mark the section, and you will calculate A value, no? So you specify the distance, A distance here, and the remaining distance is x minus A is here. Here the remaining distance is L minus x. Here it is C minus A. Here you can find the remaining distance from geometrical calculation. Okay. Now the beam is loaded. Now the beam is loaded. You will have some W Newton per meter. So the bending moment ILD diagram already known. So under the section, you draw the ILD for bending moment, and also the ordinate. Ordinate is also can be calculated using x into L minus x by L, because x value known value, L known value, so you can calculate ILD ordinate value. Again, I am drawing along this, and you superimpose the UDL. You superimpose the UDL with the available value of A and C minus A, and you just drop the lines from the loading, and you shade the portion. You shade the portion. So now the maximum bending moment at a given section is equal to area of ILD under the loading into load. So what is the area? Already I have told you, keep this is A and B, this is H. So it is like trapezoidal. So H by 2 into A plus B is the area of ILD diagram into the load W Newton per meter will give the maximum bending moment at a given section. So up to this, we have learned three conditions for UDL shorter than the span. So what are the conditions? First one, maximum negative shear force. Negative shear force means we need RB. The RB value should be fully available, so that there is no load on the section. There is no load on this span, so that all load on the other side, so that we get maximum RB. To get full RA value, that is maximum shear force, positive shear force value, your given section should not be loaded here. It should be away from the section like this to get full RA. So our head and tail is like this. Here head and tail is like this. So we can form the condition to get maximum negative shear force at a section. Place the head of the loading on the section and calculate RB. To get maximum positive shear force at a given section, place the tail on the section and calculate RA. And to get maximum bending moment at a section, first of all, place the, here I have, I'm going to write divide the condition is divide the UDL in the ratio as the section divides the beam. How the section divides the beam? Here it is x, here it is L minus x. In the same ratio, you have to divide the load. How you can divide? You mark it is a distance, and you know the total length of the UDL. So the remaining distance is C by A. So you can have a relation like this, and you can find the any one distance A or C minus A, so that you can place the load, the section, and the left side A distance and right side C minus A distance. Once the load is fixed, then the other process is to find out whether RA or RB or the bending moment. Now you have placed the load. Then find RA or RB, because the bending moment can be calculated either from A side or from B side. So conveniently you can choose any one of the option. So if you find RA, the regular procedure, taking moment about B, you can find RA value, and taking bending moment equation from this, that is RA into X minus, if it is W, means W into A square by 2 is the bending moment at XX. How I am writing? Here it is RA value. RA into X is the bending moment equation up to this point. So it is rotating like this. And here a small UDL portion is there. So it will be rotating in opposite direction. So it is W Newton per meter. So W into the length of the loading is small a. So W into a square by 2. So this is the bending moment equation from left side. You can even write the equation from the right side with respect to RB. Either any one of the value can be used to find out the bending moment. So this is the conditions to deal with the UDL longer than the span. We can elaborately see with the example in the next videos. Thank you.